So I'm going to do a revision lesson now on vectors and mechanics. I actually only got 15 minutes because I'm on a different computer. So let's just get going through this. Pause the video and have a go at the questions when you can. So the main things to remember is you've got all the SUVAC questions. They all work in vectors. The only thing that's not a vector is time. You've also got, it's worth mentioning that when acceleration is 0, you can simply just use the equation s equals ut, which is obviously part of s equals ut plus half at squared. You've also got force equals mass times acceleration. And then another equation that sometimes people find useful is this one down here. R represents position. Position, where you are at time t, equals the initial position, which we call R0 plus S. Or in other words, where you are equals where you were plus the journey you've taken or how you've been displaced. So those are really the equations which are useful to us. First thing is you should always really work in column vectors, and you should always try and draw a diagram. So feel free to pause and have a go at the question. Here's my origin. I'm over here 19.2, and that's at t equals 7. And I want to draw the path that I've taken if I can. I know that I'm moving with a velocity of 4 minus 2. So that's this sort of direction. But I know I'm passing through that point. So my path is going to look like this. I'm looking for the distance to the origin when t is 3. So there's my t is 3, because I know that I've been traveling on the path in that direction, and I'm looking for this red distance here. In other words, I'm looking for the position at time 3. So ultimately, I'm trying to find r of 3, and then I can take the magnitude of that. So I can work out now, I've got my velocity, and I've got my position at time 7. So my r of 7, where I am at time 7, is where I was, let's say at time 3, plus the displacement I've made in those 4 seconds. And the displacement made in 4 seconds is going to be my velocity times the time of 4 seconds. So r of 7 we know is 19.2. Where I was at time 3 plus 16 minus 8. Where I was at time 3 is equal to 310. And therefore the distance, the red line, will be the magnitude of that. So what I'm looking for is square root of 109. Okay, again, pause the video, have a go at the question. So going through my information, I'm going to put my fixed origin somewhere. I'm going to say I was at minus 2, 3 at start. That's at time 0. And at time 5, I'm at 13 minus 7, just somewhere over here roughly. And that means I know that I'm dealing with a constant velocity again here. So no acceleration, so it's not going to change direction. It's only going to go in the direction of velocity because it's constant acceleration. And I'm trying to find an expression for the position of A at time t. So I know where I am at 5. And I know where I was at 0. So r of 5 equals r0 plus the displacement I've made in those 5 seconds. And that gives me a displacement of 15 minus 10. But I also know that displacement equals s equals ut, or s equals ut plus half at squared, but here acceleration is 0. So this should equal u times the time that I've been displaced for, 5 seconds, which means that u will equal 3 minus 2. So I now know that this velocity is 3 minus 2. Okay, I'm told I have an additional ship B that's at 8.3 at time 10. And it's going to collide with the other one. So let's say it's going roughly in this direction, and at some point they're going to have a big collision here. And that's going to happen when time is 30. Now I know a lot about ship A, so I can work out where ship A is at time 30. So r of 30 for ship A will be where it started, plus a 30-second displacement. You could call that s of 30. And we know how to work out a 30-second displacement. We do the velocity times the time. And if we do that, we get 88 minus 57. So we now know that this coordinate is 88 minus 57. And now we can work out, sorry, there's an error in my previous labeling. That should have said 10. Thank you. Now I know I've got a 20-second change in time. I can find out what the displacement is. So R of 30 equals R of 10 plus a 20-second displacement. Call it that if you like. 88 minus 57 equals 83 plus a 20-second displacement. So that's going to be U times 20. Now in this case, they've actually called their velocity capital V. So I'm going to try and stick to their notation. And I find that capital V equals 4 minus 3. And it's only then at the end do I need to put it into the form they've asked for. I don't need to work in that form throughout. In fact, it's preferable to work in column vectors. Okay, so those first two had a constant velocity, which means acceleration was 0. We can, of course, do questions where we've added some complexity to it. So there's going to be acceleration can be considered. Final velocity, therefore, needs to be considered. Force may need to be considered. So we'll have a look at this example 4. Again, let's start off trying to draw a diagram, see if we can draw the path. Even if you find this challenging, while you're revising, try to practice this process of drawing the path because it will make it easier for you in the longer run. So I'm going to have my starting point, and I'm told at t equals 0. Now, I don't know, I'll notice it doesn't tell me where I start. So I'm just going to use that dot to represent my starting point for now. T equals 0, I know the direction my velocity is going in. I know the direction the particle is going to be going. So it's going in this sort of direction. And I know my acceleration is this sort of direction. We normally do a double-headed row. So it's going to end up going in this sort of direction. So unlike the others where I just went on a straight line in the direction of the velocity, when you have acceleration bends your path into the direction of the acceleration in the long term. So you start off traveling in the direction that you were, but the acceleration gradually bends you around until you're going in the direction of your acceleration. So that's what the path's going to look like. So this one won't be a straight line. And if you only get used to drawing the straight line ones, then you'll feel like they always are. Okay, now, the interesting thing is the wording here. We have a few different things. Find the time when the particle is traveling due east. So where on our diagram, let's do that in red, where on our diagram are we traveling due east? It's at this point here. So it's a good idea when you're reading the question to quickly note down. They normally do it the same way around, but good to note it down just in case they change it. So that red point here is the point when we are moving in an easterly direction. We are headed east, we are headed right in this diagram. And what's special about that? Well, that red vector I've just drawn is something 0. I'm going to call it K0. And what is that? Is it my position? No, I don't even know where the origin is. Is it my displacement? No, in fact, I sort of appear to be above where I started. It's my velocity. I'll just call it velo rather than u or v at the moment. So my velocity is K0. So my velocity has no displacement. So this is now what I need to work with when I'm trying to find out traveling due east. So I can go to my SUVAT. I know my acceleration. I know my initial velocity. I know my final velocity must be K0. And I know the time is the thing I'm looking for. So I want the equation which doesn't involve S. V equals U plus AT. Notice I'm underlining the things which are vectors. K0 equals minus 2, 3 plus 3 minus 1 times T. It might seem like it's two unknowns, I can't solve it, but with a vector equation, you can take a single line out of it. So for example, I can take the bottom line, 0 equals 3 minus T, and find that T is equal to 3. If I wanted to, I could then therefore work out that K was 7, which means that my velocity at that point was 7, 0. So you can see that means it's moving At that moment, instantaneously at that moment, it's trying to move every second 7 to the right and 0 up or down, which means at that moment, instantaneously, it's trying to head east. Okay, so that's if it's anything to do with find the time when it's traveling east, moving east. That's all to do with velocity having a 0 y component. Find the time the particle is due east of its starting point. So on my diagram, due east of its starting point would be here. So that means its displacement at that point is something 0. So now we can work with our displacement equations instead. So we can go to S equals ut plus half at squared, plug in our u, plug in our a, and solve and make that equal to k0 and solve to find t. So that's for part B. Now we're told that we started at 10.4. And that means our origin is going to be somewhere, slightly annoyingly, down here. Now it's saying find when we're due east of where we started. So that looks to me to be about here. So what is it now that has a 0 y component? It's not my velocity. It's not my displacement from where I started. It's my displacement from the origin, or in other words, my position. So at this point, the position equals k0. So for this section, I'm going to say r equals r0 plus s. R0 was 10.4 now, plus s, which is going to be ut plus half at squared, 10.4 plus minus 2, 3 times t plus a half 3 minus 1 t squared, and that's now going to be equal to k0. And again, we take the bottom line and solve for t. So a quick reminder, these are your key equations. If it's traveling north, let's say now, if it's traveling north, that means velocity equals 0k. K would be greater than 0. If it's moved north or displaced north of where it started, that means displacement is 0k. And if it's north of the origin, or north of 0, 0, that means position is 0k. And obviously, if you started at the origin, that would also mean your displacement was greater than 0. So these are the different key aspects, and it's worth practicing these things. Big thing to do in your revision, in your practice, try to draw diagrams.